Creating a solar panel involves a detailed and intricate process that transforms raw materials into a functional device capable of converting sunlight into electrical energy. This process includes several key stages, such as obtaining the raw materials, manufacturing the photovoltaic cells, assembling the cells into panels, and testing and installation. Understanding each step in detail helps to appreciate the complexity and innovation involved in making solar panels. To begin, the primary material used in making solar panels is silicon, which is abundantly available in sand. Silicon is a semiconductor, which means it can conduct electricity under certain conditions. This property is essential for the operation of solar panels. The first step is to extract and purify silicon from sand. This involves heating the sand at high temperatures in a furnace to obtain silicon dioxide, which is then refined to produce high-purity silicon. This silicon is the base material for the PV cells. The purified silicon is then processed into silicon wafers. This step begins with melting the silicon in a crucible. Once melted, the silicon is carefully cooled and solidified to form an ingot, which is a cylindrical block of silicon. This ingot is then sliced into thin wafers using a wire saw. Each wafer is only a few hundred micrometers thick, but it forms the basic building block for the PV cells. This slicing process must be extremely precise to ensure the wafers are uniform in thickness and free of any cracks or defects that could affect their performance. After slicing, the silicon wafers undergo several treatments to enhance their electrical properties. First, they are cleaned to remove any surface impurities. This cleaning process typically involves using a series of chemical baths that remove organic contaminants, metals, and other impurities. Then, the wafers are doped with other elements to create a p-n junction, which is crucial for generating electricity. Doping involves adding small amounts of phosphorus or boron to the silicon. Phosphorus creates a negative charge, known as N-type silicon, while boron creates a positive charge, known as P-type silicon. When these two types of silicon are placed together, they form an electric field that can generate electricity when exposed to sunlight. The next step is to apply an anti-reflective coating to the silicon wafers. Silicon naturally reflects a significant amount of sunlight, which reduces the efficiency of the solar cells. The anti-reflective coating helps to reduce this reflection, allowing more sunlight to be absorbed by the cells. This coating is usually a thin layer of silicon nitride or titanium dioxide, which not only reduces reflection but also gives the solar cells their characteristic blue or black color. This step is critical for maximizing the efficiency of the solar cells, as even a small reduction in reflection can lead to a significant increase in the amount of electricity generated. Once the wafers are prepared, they are ready to be assembled into PV cells. This involves attaching metal contacts to the front and back of each wafer. The front contact, typically a grid of thin metal lines, allows light to pass through to the silicon while also collecting and conducting the generated electricity. The back contact is usually a solid metal layer that helps to conduct electricity out of the cell. These contacts are usually made of silver or aluminum. The process of attaching these contacts requires precision and care to ensure that the cells operate efficiently and reliably. The PV cells are then tested to ensure they meet quality standards. This testing involves exposing the cells to light and measuring their electrical output. Any cells that do not meet the required standards are discarded or reprocessed. The remaining cells are then ready to be assembled into solar panels. This testing process is crucial to ensure that only the highest quality cells are used in the final panels, as even a small defect can significantly reduce the overall efficiency and lifespan of the panel. To assemble a solar panel, multiple PV cells are connected together in series and parallel to form a module. This involves soldering the metal contacts of each cell to create an electrical circuit. The cells are then encapsulated in a protective material, usually a layer of ethylene vinyl acetate, which helps to protect the cells from moisture and mechanical damage. The encapsulated cells are then placed between a layer of glass on the front and a protective backsheet on the back. The entire assembly is then laminated to seal and protect the cells. This lamination process not only protects the cells from environmental damage but also ensures that they remain properly aligned and securely bonded. After lamination, the solar panel is framed to provide additional protection and structural support. The frame is usually made of aluminum, which is lightweight and resistant to corrosion. The framed panel is then fitted with a junction box on the back, which houses the electrical connections and provides a point for connecting the panel to the rest of the solar power system. The junction box also contains diodes that prevent the reverse flow of electricity, which can damage the solar cells. The final step is to test the completed solar panel to ensure it meets performance and safety standards. This involves exposing the panel to simulated sunlight and measuring its electrical output. The panel is also subjected to various environmental tests, such as temperature cycling and humidity testing, to ensure it can withstand the conditions it will face in the real world. This rigorous testing process helps to ensure that each panel will perform reliably and efficiently over its expected lifespan. Once testing is complete, the solar panel is ready for installation. Installation involves mounting the panel on a suitable structure, such as a rooftop or a ground-mounted frame, and connecting it to an inverter and the electrical grid. The inverter converts the direct current electricity generated by the solar panel into alternating current electricity, which can be used by household appliances and fed into the electrical grid. Proper installation is critical for ensuring the safety and efficiency of the solar power system. Creating a solar panel is a complex process that requires advanced technology and precise engineering. Each step, from purifying silicon to testing the final panel, is crucial to ensure the efficiency and reliability of the solar panel. Understanding this process highlights the innovation and effort involved in harnessing the power of the sun to generate clean and sustainable energy. The manufacturing process also involves careful consideration of environmental and safety standards. The chemicals used in cleaning and doping the silicon wafers, as well as the materials used in the encapsulation and framing processes, must be handled and disposed of properly to minimize environmental impact. Additionally, the production facilities must be designed to protect workers from exposure to hazardous materials and ensure their safety throughout the manufacturing process. The development of solar panel technology continues to evolve, with ongoing research and innovation aimed at improving efficiency, reducing costs, and minimizing environmental impact. Advances in materials science, such as the development of perovskite solar cells, hold promise for increasing the efficiency and lowering the cost of solar panels. Additionally, improvements in manufacturing processes, such as the use of automation and advanced quality control techniques, are helping to increase production efficiency and reduce waste. The installation of solar panels also plays a critical role in their overall efficiency and performance. Proper placement and orientation of the panels are essential for maximizing their exposure to sunlight and ensuring optimal energy production. Factors such as shading, roof angle, and geographic location must be carefully considered during the installation process. Additionally, the integration of solar panels with other components of the solar power system, such as inverters, batteries, and monitoring systems, is crucial for ensuring reliable and efficient operation. The use of solar panels has significant environmental benefits, as they generate electricity without producing greenhouse gases or other harmful emissions. This makes them a key component of efforts to reduce carbon emissions and combat climate change. By providing a renewable and sustainable source of energy, solar panels contribute to the transition away from fossil fuels and towards a cleaner, more sustainable energy future. In conclusion, creating a solar panel involves a detailed and intricate process that transforms raw materials into a functional device capable of converting sunlight into electrical energy. Each step in the process, from extracting and purifying silicon to assembling and testing the final panel, requires advanced technology and precise engineering. Understanding this process highlights the complexity and innovation involved in harnessing the power of the sun to generate clean and sustainable energy. As technology continues to evolve and improve, solar panels will play an increasingly important role in meeting the world's energy needs and addressing the challenges of climate change.